Is the presentation visible now? Is the presentation visible?
Yes, sir.
So we have been discussing about typed lambda calculus, and that is associating a type with every lambda expression, which if they are syntactically correct, we call these expressions as pre-expression. And if after the type checking, the expression can get a clear type, then we say it is an expression, right? We have talked about that. Now, we started with associating type with simple lambda expressions, which we had known earlier, which is called the simply typed lambda calculus, which has constants, variables, and function mapping. And we have parenthesizing of types giving the same type. Interestingly, what then we developed is a collection of type builders. Function also is a type builder, but that was the fundamental in lambda calculus. Now we are building types which are very close to the kind of type builders we see in most of the programming languages. So the first type that we built was a tuple type, which is a cross product of n types. That is, it is a tuple, ordered tuple of variables, values, so that that entire entity can be treated as one unit. And we saw that tuple type has a good requirement in terms of handling n-ary functions. A function has n parameters, then we can pass that n tuple to the function, so that every component of the tuple can be internally projected out and used by the function, but the function per se has only one parameter. So with the tuple, we get a very good mechanism by which we can restrict all our studies to functions of single parameter only. So that is the tuple type we introduced. Then we introduced a record type, where again we have a collection of values, variables of n types t1 to tn, but with the exception that every component now is not identified by its position in the tuple, which is position in the collection, which is in the tuple type. Rather, it is identified by a label, and which is very similar to the struct or class that we have in C, C++. So we have labels L1, L2, L3, and so on, and each label has an associated type, and that is the component of a record type, and we use the dot notation, the usual dot notation, to take out components. So we have a record type. The next that we did is something very interesting, and as we'll see, it is very useful, where we say that we are doing a union, disjoint union of n types, called the sum type t1, t2, tn, where if I have a variable of some type, then it has only one quantity which is of any one of these n types. But at a time, it will have only one entity of one of these types, which is very similar to union used in C programming, or specialization used in I'm sorry, inheritance specialization used in C++. If you actually go through the slides of these extended types, in a new presentation will be uploaded on the Moodle for this particular module, you will see that I have shown several examples where a sum type can be represented. What is a classical way of representing that in C programming or in C++ programming and so on? What are the corresponding models there? But the basic fact which makes the sum type uh, quite powerful is the fact that I know a domain of types to which the value can belong, but at any point of time, the value belongs to only one of those types. So this is a kind of, I've shown through those examples, is kind of a parallel to the modeling of inheritance hierarchy in lambda calculus effectively. So we have seen the builder of that. There is an injection function to which I can give a particular index for the type in the sum type. And at that index, with that index, a value of that type ti will be injected in the expression, and the expression then contains only one value, which is of type inheritance. Then certainly the you know uh, dynamic polymorphism will remember that, which effectively turns out to be the virtual function table pointer, which kind of becomes a tag. And then we have seen the use of this sum type in terms of a case statement, which kind of can be called as a type switch, that is given at a variable of type t1 plus t2 plus tn, some type. We actually dig in to see which value, the value of which type ti has been injected in this variable. And depending on that type, we take an action on that ith value. And so here we have a case, or we have a switch which is based on type. So this is called a type switch or type dispatch, which is exactly what you do in terms of dynamic polymorphism in C++. So you can see the correspondence, and I have given at least 5-6 examples, complete worked out codes in the revised presentation, where you will be able to see that. Then we have seen, then we have introduced a reference type, which given a variable talks about its address type, or given an address talks about its value type by val operation and so on. And we also mentioned that array type, which is very common.
Excuse me, sir.
Yes,
The slides are not visible, sir.
slides are not visible. They have
No, sir.
stopped showing. Okay, I have not changed any slide though. Anyway, I'll stop and share again and hope that it will work. Is it visible now?
No, sir.
It's still not visible?
No, sir.
Okay. Let's so let me just drop out of the class and come back again, hoping that that should work. But if I put the camera on, you can see me, right? I put the camera on. Can you see me?
No, sir.
Oh. Let me go out and try. Can you see me now?
Yes, sir.
Yes, sir.
Let's see, hopefully now the presentation will also work. Can you see the presentation?
Yes, sir.
So, so beyond the reference type, I mentioned that array type, which is very common in all programming languages, will also be required. But array type basically internally needs a model for the memory, because it can store arbitrary number of values. All of these that we have discussed so far stores only a given number of values. So array type needs a little bit of more detailed modeling in terms of memory. So we'll handle that at a later point of time when we talk about semantics and we actually bring in memory in the whole space. So given these, I extend the type expressions. So TC continues to be a collection of type constants as before. And what we add is L, which is a infinite collection of labels. This is required for the record type. So I add L to that. And these are the type expression extended from the earlier set, which was just C, T1 maps to T2. Of course, I missed the parenthesis case, but that is there, trivial. And then we have the tuple type, the record type, the sum type, and the reference type. I've put two more. One is called a void type. Void kind of is a null tuple. So it is kind of a placeholder for the type expression. It's kind of the zero of the type system. It is a placeholder which says that there's no type, right? So uh, if there is no type that we know or that I need, then instead of keeping that blank and trying to deduce something gets very difficult. So we specifically put a type void in that place. And what we add further is a command type, which is nothing but certain types of lambda expressions which are very common in programming languages, and we will include them. Let us see. Let me go to the next slide. So void type is a type of zero tuples. For example, you have C functions where you can return void. Return type could be void, which means that it does not return anything. Or you have procedures in Pascal or in Fortran where there is no return type. So that return type will be treated as void. It has only one. So this type has only one value, only one constant, which is a null tuple. Then we have function types, tuple types, record types, sum type, reference type. This we have already seen. Then you have a command type, which represents certain types of statements and expressions like assignment. So let us see through this detailing. So let us now redefine the collection of pre-expressions. We had done that before for simply typed lambda calculus, which is the first line here. A pre-expression could be a constant from TC. It could be a variable from the collection of expression identifiers. It could be now a void constant. It could be a lambda abstraction where the parameter has a type T. It could be an application, function application, M applied onto N, and it could be a parenthesis. So this is your the coming from the simple type lambda calculus with the addition of the void. Now we can have types which are, this is an expression of tuple type. You can see the tuple notation, angle brackets. So if M1, M2, Mn are lambda expressions, then a tuple of them is a lambda expression as well. If M is a tuple type, then proj I on M will give the ith component of the tuple. So this is also a lambda pre-expression, proj I M. This is an expression. Next is an expression for the record type where label L1 is of type T1, has a value lambda pre-expression M1 and so on. Label Ln has type Tn having a value of lambda pre-expression Mn. So this is a record type, and if I have M as a record type, then M.Li will give me Mi, that ith expression for the record. For the sum type, we have the injection operation, which gives you a lambda pre-expression. I'm injecting M as the ith component in the sum type. And then I have this type switch, which is case M of x1. You have seen this syntax. So depending on which value of which type has been injected in M, I switch to that corresponding type and take out that value as xi, and which will be of type ti, and evaluate the corresponding ei. So this is another lambda pre-expression. Then we have ref m, which is given a lambda expression of a value type. I can get its reference type. Given a lambda expression of reference type, I can get its value type, the reverse of these two. And I have a null reference, which is a little bit of a unique concept, because as we know, in at least in C++ terms, there is no null reference which is allowed. It's more like a pointer in that sense, but it's actually called a reference and treated as a reference here. Then we have example pre-expressions of the command type. So one that we put here is if B, where B is a Boolean type, then the pre-expression is M, otherwise the pre-expression is N. Now, I know you will not get surprised by this, because when we talked about the lambda expressions, there itself, we had shown that using lambda expressions, the first selector and the second selector, how we can create notions of Boolean constants in terms of lambda expressions, and how we can create the if kind of command, or and or kind of not kind of gates and so on. So we can using that, we can very safely assume that we have a command pre-expression, which is basically an if then else statement. Then you have a special statement which is called no operation. So it is a placeholder for command, but it's again like in the command space, it is a zero of the system. So no op basically says that there is no operation to be done. Those of you who are familiar with assembly language will know that assembly languages often have no ops, nop in some way or other, where just a cycle goes, but nothing is done in the ALU or in the instructions per se. You have no operation in representation of C or C++, which is just a semicolon. If you just put 3 semicolons, then you have 3 statements, but those are null statements. They do nothing, right? So that's similar model is no op in the lambda pre-expression. Then you have what is called an assignment. So a lambda pre-expression of pre-expression M is assigned to a lambda pre-expression N, and this assignment becomes a new lambda pre-expression. So we allow assignments to happen. The consequences of assignments will unfold when we take onto the actual semantics of these, denotational semantics of these expressions. But for right now, we are just talking about the type checking. So we'll see that if we have to do an assignment, what kind of type checking will apply. And finally, in the command, the fourth and the last is sequencing of commands. So if M is a command and N is another command, so if M is a command pre-expression and N is another command pre-expression, then you can sequence them as M semicolon N. M, first M, then N, right? So this sequencing is again parallel to the sequencing of statements in C, C++, Java, whole lot of languages, right? So these are the pre-expressions of extended typed lambda calculus. And in terms of this, we will see the type checking rules. Right. So on to the next slide. There is nothing new. It's whatever I have said. I have put them in statements here so that you don't have difficulties when you are studying. Of course, a significant, so so kind of if you get back to this collection of pre-expressions, you can see that all variety of data types have already been modeled with the exception of array. And we have the variety of command expressions, pre-expressions also modeled, which you see in the programming languages, with only one significant exception, which is you do not have a loop. There is no loop construct. Now, loop, as you know, is actually equivalent to recursion, right? If you have recursion, you represent loop. If you have loop, you can model recursion. So this is required for completing the expressive power. So what we will do is we know that using the Y Combinator, we can handle recursive functions in Lambda. So we'll be able to have pre-expressions which are basically can use Y Combinator and thereby have functions which are recursive. So if there is a need for a loop in our common logic building, we can always model that in terms of recursive functions and get the same expressive power. And it is not explicitly necessary to have loops. Though going forward later, when we talk about the navigation between operational and denotational semantics, we will show that how loop can be interpreted in the Lambda paradigm as well. But it certainly stays simpler if we don't allow loops, but we just handle any repeated logic in terms of recursive functions alone. Right. So this next will be the type checking rules. Before that, let me just go back once to you to see if there are any questions, or you are okay with the extended type lambda calculus, its type expressions and its pre-expressions. Is there any question, friends? Seems no. Okay. So let me go ahead and talk about the type checking now. So I'm back to the slide. So the first few type checking rules, as you know, that we have talked about type checking rules in case of simply typed lambda calculus. And the premise that we have is given a lambda pre-expression, we find out what are the free and what are the bound variables therein. The bound variables will get their type from the binding on the expression, and the free variables are associated with the type in a static environment. So we assume that the whole type checking is done with reference to a static environment E, and that is what we keep on. So initially we start with an E which may be an empty set, and then as and when more and more variables assume different types, we keep on putting them in the static environment, and in that context we keep on checking the types. So we have seen this for the first simply typed lambda calculus. This is the identifier rule, which does not have a antecedent. So it says that if x is of type t, then x is of type t. So if x is of type t, then you just add it to the environment. So you have x is of type t. Then again, the constant type checking rule, which does not have an antecedent, which says that C is in the environment. So you can assume, I mean, you know its type whenever you know the constant. So you can assume that added. We talked about function then, and we said that lambda x of type S and body having body M, the type of this will be decided based on the type of X, which is S. So you add that to the environment. And then if the type of M is T, then the type of this lambda abstraction is S going to T. So this is a function S mapping to T, which is quite obvious. And this is we have seen the use of that, and we have checked and deduced types based on that. Similarly, for application, if M has a type S to T, which has to be the function that applies, and N has type S, which has to match with the domain type of the function, then M applied to N has a type which is T. Parenthesis is simple. What got added is also that fact that there is no precondition, but void this null tuple is of type void, which is by definition we have created, and that belongs to the environment. Type. In the tuple type, let us so the precondition is, the antecedent is that I have n pre-expressions, m1, m2, mn, and each pre-expression mi is of type ti. So I say that in the environment, if mi is of type ti for all I from 1 to n, so I basically have m pre-expressions having corresponding n pre-expressions corresponding to n types, which could be same, they could be different, they could be anything. Then the type of the tuple is the cross product of their types in this order. I had lost connection. Can you hear me now?
Yes, sir. Now you are audible.
So I'll go back again. I hope the slide is visible. So I don't know how much you missed. So I'll again repeat for the tuple type type checking rule. So the antecedent, the precondition is I have n lambda pre-expressions m1 to mn of respective types t1 to tn. So that is what we put in the
Excuse me,
precondition.
sir. Slides are not visible.
Not yet?
No, sir.
Oh my God.
They're
What
visible for
goes on? It was visible for some. Is it visible now?
Yes, sir.
Not yet, sir.
For some, I think it is visible. For some, it is not. Is it visible, Showman? No.
No, sir.
Let me again go out and try. Is it visible now?
Not yet, sir.
What is wrong? Let me just check a poll. If I put my video on, is the video visible?
Yes, sir. Video is visible.
But the slide is not. So, could you please raise your hand when last time I shared the presentation? Could you please raise your hand if you could not see the slide? So everybody got to see the slide. It's only Showman who was missing it, is it?
Sir, I haven't seen the slide.
Mm-hmm. But nobody is raising hand. Could you please raise the hand if you could not see the slide? Seven could not see the slide. 8, 9. Oh, that's peculiar. Some people are not seeing, but rest others are seeing. Okay, let me disconnect and try once more. I'm sharing again, hoping that this will work now. Can you see?
Not
Yes, sir.
okay.
You can see, na? Can you see the slide?
Sir, in my end, I am not seeing, but
Hmm.
are saying they can see.
Okay, okay. So what this is a peculiar problem I think we are having for the first time, that thrice I've tried to go out and come in and do that. From next class, what I'll do is I'll keep the presentation shared with you earlier. So at least if you are not being able to see here, I can speak out the slide number and you should be able to follow. I'll follow that, because this is getting too much of time we are losing in just managing this. Anyway, so this is the tuple type. Then we have, for tuple type, we also have the projection operation. So which says that if there is a tuple of type T1 cross T2 to Tn, a lambda pre-expression for the tuple, then I can project the ith expression out of the tuple by doing proj I on M, and that will be type Ti. Now, between the tuple type checking rule and this projection rule, just note a difference in terms of the rule structure. In the tuple rule, the precondition mi is of type Ti has to hold for all n components. And only then, if all of them m1 is of T1, m2 is of T2, then and mn is of Tn, only then the consequence tuple type can be checked. Whereas in projection, it actually represents n different type checking rules. There is one rule for I being 1, which says given m is of type tuple T1 to Tn, proj1 on m is of type T1. Then there's another rule which is for I being 2 and so on. So there are actually n rules. So you'll have to realize that that here is a short way of writing actually n different type checking rules belonging to, corresponding to n different components of the tuple. Next, we have the record type, which is very similar. That if you have each expression of the record component mi is of type Ti, again for all n components, then the whole record, the lambda pre-expression for the record has the type of the record. So all that you are saying is m1, m2, mn are removed. So level L1 is of type T1, Ln is of type Tn, and so on. And similarly, selection is something very similar to projection of tuple type. So if you have a record type, if you have a lambda pre-expression m of the record type L1 to Ln, then you can take out the component Li from m, which will be of type Ti. And again, like projection, this is actually representing n different rules, not one rule. Then we have sum type. So for sum type, if we have expression m of type Ti, there is, so here it's not for all, there exists. So there exists some I for which m is of type Ti. Then I can inject that m into the sum type by this injection, and the resultant type of the lambda pre-expression will be the sum type. This is something which we have intuitively seen. We are just formally writing them in terms of type checking rules so that we can apply and get type checked for any lambda pre-expression of the extended type. So if for an I have m is of type Ti, then I can inject that as a ith component in the sum type to get a sum type lambda expression. Finally, if we have there is the type switch or case. So if m is a lambda pre-expression of the sum type, and I have x of type Ti available, then for this case expression, I will have ei having the type u. That is, if my component xi as injected in m is of type Ti, then I'll select, for example, if it is x1 is of type T1, then the expression is E1, which has a type U. Now, here, obviously, there are n different expression E1 to En. So you would ask that what if E1 has a different type than E2? Well, in that case, the type checking fails. So the basic condition which I've written in red, the case expression require the types of all branches be the same type. E1, E2, En all must be of the same type U. And so that irrespective of which particular type is taken in this type switch, the resultant expression will have only type U. So if xi is of type Ti and ei is of type U, you can see in U we are not putting any I, it has to be the same. Then the case expression has a type U. And obviously injection could have happened in any one of the ith component. So you have again I rules for doing this. So these are the type checking rules up to this point. Then you have the type checking rule for reference, which is very easy, that if m is of type t, then ref m is of type ref t. For the null reference, you have null is of type ref t. So null reference in conceptual sense belongs to any type. So for any type whatsoever, unspecified, if I take a ref t, if I take a reference of that type, then null will be an element in that. So without any precondition, null is of type ref t for any type t. The value operator. So if m is of reference type, then val m is of type t. This is obvious. No op in the command. Obviously, no precondition. No op is an element of command, is of type command. Assignment n assigned m needs that if n has a ref type t and m has a type t, then this assignment has a type command. Mind you, these have to be, so if n, the left hand side, is ref of some type t1 and right hand side m is of some other type t2, then the type is not defined, then the type will not get checked. So this is kind of a strict type checking. So by this you say that int values can only be assigned to int variables. Double values can only be assigned to double variables. Some structure value can be assigned only to that structure type, and so on. So the strict assignment type rule that you have to apply at this point. Finally, you have the if statement. So if b is of type Boolean, m is of type t, and n is of type t, then if b, then m, else n, this pre-expression is of type t. Again, like the case example, you have to note that m and n, the type of the two different true and false branches, have to be the same. If they are not same, the type checker fails. So if both are of type t, then b being Boolean, also if b is not Boolean, the type checker fails. If these preconditions hold, then the type of the if command is t. Finally, sequencing. So we say that if m is sequenced of before n, so you evaluate the pre-expression m and then you evaluate the pre-expression n, whatever that means. We still do not have, in terms of lambda calculus, we still do not have the sense of evaluating one before the other. I mean, we are trying to put that in the calculus now. So in this sequencing, if m has a type s and n has a type t, then m sequenced n has a type t. So which says that if I sequence one lambda pre-expression before another, then it is the type of the later lambda pre-expression which becomes the type of the whole sequenced lambda pre-expression. Right? So this is, so for all these different, if I quickly go back a couple of slides, so these were my type expressions, and for based on that, whatever pre-expressions I talked of, for each one of them now I have a type checking rule, exactly like I had for the simply typed lambda calculus. So if I write any lambda pre-expression involving all these types and operators, then I'll be able to using the type checking rules, I'll be able to check its type and say that whether it has a decidable type. If it has, then that pre-expression becomes an expression. Otherwise, it just remains syntactically valid, but otherwise not an expression in lambda calculus. Certain rules can be I mean, can be derived from this type checking rules. For example, for n-ary functions, we will always use, or more often we will use the typical function notation id1 colon id2, id1 of type t1 and so on, which is in our using our tuple abstraction is actually an abstraction of this form where you have one argument of the tuple type, and then you take out different components of that argument while you apply this on M. So for n-ary function, we can have a revised type checking rule where you say that if this collection id1 of type id2, t1, id2 of type t2, idn of type tn, if this collection is present in the environment, then M has a type U, where this particular lambda abstraction is from the tuple type t1 to tn mapping to U. If I have this type, then the result. So this is just kind of a syntactic sugar, just to in many places make it easier for us to write. So while we might continue to write the n-ary functions in the way we are more familiar with, but internally we know that they are actually being meant to be functions of single variables only, and we can do our deductions based on that. So this rule comes handy in that respect. The other syntactic shorthand that we use is called the let expression. Let expression is written in this way, particularly for this is for saying that if I have a lambda abstraction on n, lambda x of type tn, and that abstraction applied onto M, right? So what you do, you take you will take M x and substitute in n, right? So that's and you know that all the substitution rules and so on. So this is typically written in this manner: the let x be of type t, then you put M in end n. That's what you're doing. You're putting M in n, replacing x, substituting x. So this is a more programming like syntax for this very pure lambda expression. So you take the parameter and the type first. So you let, then you put an equal to or assignment, whatever, equal to symbol, let's say, or defined symbol. This means that M will be replaced for x in n, and let ends with an end. So thus introducing an identifier for an expression is modeled by writing a function like this. So naturally, the rule for the let expression would be that if x has a type t in the environment, then n has a type s. If M has a type t, and if you have, then you will have all of this whole of s let expression have the type s. So we have seen this in terms of, if this is kind of combining the abstraction rule and the application rule. You're just combining them together. So you're saying that x is of type t and n has given that n has a type s and m is of type t. So then it's an application of this t to s, your t to s, and on m, which is of type t. So your resultant type will have to be s. So this is what you'll get. Okay, so this is all about the type checking rules. Let me go back and see if you have any questions. Any questions, friends? So because we will be closing on this module now, so beyond, so this is the third major component of lambda calculus that we have done. We started with the syntax. We did what is correct lambda expression and so on. Then we talked about semantics, which is what the lambda expressions mean. So in lambda expressions themselves, which was the fundamental premise of using lambda expressions to mean lambda expressions, and we brought in the notion of reduction and the normal form. And then we have typified the lambda expressions now and extended that to come very close to our programming languages, right? So this is what we have achieved so far. So if there is any question we can address, otherwise there doesn't seem to be anyway. So we will stop here today. In the next class, I will talk about, I'll just little bit sidestep and talk about lambdas in C++. So what you have seen besides this, formal development of the lambda calculus and its type system and so on. The other that you have seen are examples of some purely functional programming languages like Haskell scheme, so on, which are purely based on lambda calculus, right? So they are interesting in terms of not using variable values. They're doing computations in constant, and they happen to be easier to verify and so on. But certainly they are not the language of choice for most of us. So what I would like to discuss and show you that in a language like C++, which has been prevalent as a strong programming language, particularly on the systems side and so on, for such a long time, you now have the introduction of lambdas. And introduction of lambdas particularly make certain aspects of C++ language, which is metaprogramming and template metaprogramming, really powerful. So you continue to use it as a procedural language, as an object-oriented language, exactly the way you had been doing. But what you bring in now is the whole concept of lambda expressions and the evaluation of lambda expressions and so on, and give it a different kind of power, which particularly help write several function codes which can be generic in nature. So we will take that discourse in the next module, and then come back to talk about type systems, which are systems which actually check types in a little bit more I should say more common programming languages. What we have presented is also a type system, because once you have the rules and you know how to apply the rules, the ladder diagram and all, you can always write a system which, given an expression, checks its type and finds out the type or says that type cannot be deduced. But life gets different when you come to common programming languages, because you need a simpler semantics, you have a historical legacy of writing things in a certain way, and a big component called memory, the persistence, come in the way of actually transferring a value from one expression to the other, right? An expression creates a side effect on the memory of setting the variable to a value, and then that side effect impacts the value of some other expression, right? So that's the kind of, so we'll get into slowly into that. So I think since there is no more question, we'll close here now. And on Wednesday, we'll start with lambdas in C++. I'll give someone to upload the presentation beforehand, so that keep that ready with you. So in case this visibility problem is happening too frequently as it did today, you should be able to refer to your local copy and still keep on following what I'm saying. Okay.
Excuse me, sir.
Yes.
Sir, in the last test on Wednesday, there was a question, I guess, which had all the options wrong.
Well,
I believe.
please send a mail to me with copy to Shoman and Srijani. We will look into it.
Yeah, okay.
Okay, what you think, what is it, which question you are talking of, and what you
Yeah,
think of that, right? Please
yeah, yeah.
send it. we'll certainly look into that. It is always possible. That could always be a mistake.
Yeah.
Like
Yeah.
we are also human, so we could have made a mistake. Okay.
Yes, sir. Thank you, sir.
Okay. Okay. By then, have a good day. See you on Wednesday.